You know, medical radiation is an absolute modern miracle. It lets us see right inside the human body, it helps us destroy cancer. But what happens when one of our most powerful healing tools is also invisible and, yeah, potentially dangerous? We're going to pull back that curtain and look at how we safely handle this incredible force. All right, so here's our game plan. First, we're going to tackle that central paradox. Why do we use something that could be harmful to heal? Then we'll get into what radiation actually does to our bodies. From there, we'll uncover the three simple rules that are the bedrock of safety, see them in action, and finally, wrap up with what all of this really means for you.
So let's dive right in. The whole issue really is a paradox. We've got this amazing, life-saving tool, and the more we use it, the smarter we have to get about managing the risks that come with it for everybody involved.
Which brings us to the big question that's probably on your mind. How in the world do doctors use something we know can be harmful to actually heal people? It sounds like a total contradiction, but believe me, it is all about control and understanding. So here's the challenge. Our use of medical radiation is just skyrocketing. I mean, incredible things like CT scans and complex surgeries happening inside our blood vessels are pretty routine now. And that means more exposure for patients and for the medical staff. But the thing is, sometimes the safety training hasn't quite kept up with the tech. That's a gap we really need to close.
Okay, so to really get a handle on how we stay safe, we first have to understand the risk itself. What is radiation actually doing inside our bodies on a biological level?
The kind of radiation we're talking about is called ionizing radiation. It sounds complex, but the idea is actually super simple. It's just energy that's strong enough to physically knock an electron right out of an atom. And when that happens inside a living cell, well, that can cause damage. It's basically a physical collision on a microscopic scale.
Now, that damage leads to two totally different kinds of effects. And honestly, the best way to explain it is with an analogy. On the one hand, you have deterministic effects. Think of these like a sunburn. They happen because a whole bunch of cells die. There's a certain threshold. Once you cross it, the effect shows up, and the more radiation you get, the worse it is, just like a sunburn. On the other hand, you have stochastic effects. This is way more like a lottery. A single cell gets its DNA damaged, mutated. There's no known safe dose. The more exposure you get, it's like buying more lottery tickets. The higher your chance of winning something terrible, like cancer. So one is about certainty. The other is all about probability. So, how do we protect ourselves from all that? Well, it all comes down to three incredibly simple, but really powerful principles. This is the absolute core of all radiation safety.
And here they are: time, distance, and shielding. It really is as simple as it sounds. Spend as little time as possible being exposed, get as far away from the source as you can, and put something protective, like lead, between you and that source. Literally every safety protocol is built on these three pillars.
Let's just zone in on distance for a second, because it is way more powerful than you might think. It's all about something called the inverse square law. All that really means is that your exposure drops off like a rock as you move away. So think about it like this. If you just double your distance, say take 2 steps back instead of 1, you don't just cut your exposure in half. Nope, you cut it all the way down to 1/4. It's an exponential drop, which makes distance your absolute best friend when it comes to radiation safety. Okay, so we've got the 3 golden rules: time, distance, and shielding. But what does that actually look like in a real high-stakes medical suite? How are these simple ideas put into practice with such incredible precision? First off, you should know that this is all highly, highly regulated. This table shows the annual dose limits measured in something called millisieverts, or MSV, and just look at the difference. A person who works with radiation for a living is allowed a dose of 20 MSV a year. But the limit for you or me, the general public, it's just 1. Now, for a little twist you might not see coming. We've all seen it, right? That classic image of the heavy lead apron being draped over a patient. For more than half a century, this was considered the absolute gold standard for protecting people during an X-ray. It's just common sense, right? Well, it turns out science is always evolving. And with today's super smart imaging machines, that lead shield can actually trick the system. The machine sensors see the shield, they think the image is too dark, and they automatically pump more radiation into the patient to get a better picture. So a practice that was designed to protect can sometimes do the exact opposite. It's a perfect example of why this field is always being updated. And beyond shielding, medical teams have this whole toolkit of other techniques. Instead of a steady, continuous beam, They use short, little bursts. They use something called collimation, which is just a fancy way of saying they narrow the beam down to only the tiny area they need to see, like a little spotlight. They also position everything perfectly to cut down on any stray radiation. And they try to avoid using magnification, because just like zooming in with your phone's camera, it can easily double or even triple the dose. It's this constant, active process.
Okay, so we've seen the physics, we've seen the professional techniques, but let's bring all this back home to the most important person in the room, you. What does all this mean when you're the one on the table? Let's put some numbers to this to really get some perspective. A single chest X-ray is a teeny tiny dose, just 0.02 millisieverts. A long-haul flight, you get 5 times that just from cosmic rays. And we all get about 3 millisieverts every single year just from natural radiation in the environment. Now, a CT scan of your abdomen, that's quite a bit more, around 10. So the key takeaway here is that while medical doses can be significant, they exist on a whole spectrum of exposures we get in our lives. When you strip everything else away, it all boils down to 2 core principles for any medical procedure with radiation. The first is justification. Is the scan truly necessary? Is the benefit going to outweigh the risk? And the second is optimization. If it is necessary, is every single step being taken to use the absolute lowest dose possible to get the job done? So I'll just leave you with this thought. Now that you understand how safety works, the ideas of justification and optimization, what's one question you might ask at your next medical scan to be an informed partner in your own healthcare?